Hey everybody, in this video I'm going to go over a couple more parts of that Elements and Molecules of Life worksheet that you were working on, and it should help you, especially this first part of what I'm going to say with number 9. So I want to remind you about electronegativity, that word meaning how badly an atom wants electrons or an element's affinity for electrons. And I had mentioned to you the noble gases. So if we had an atom of helium here. Helium is one of the noble gases. That's that far right column or group on the periodic table. Remember, these noble gases, they have filled outer shells, so they do not want any electrons at all. They've got no electronegativity in that sense. If one of these noble gases happened to cruise by another atom of whatever kind, it's not going to interact at all because this does not want to enter into any electron sharing or transferring relationships, right? So noble gases will not ever enter into compounds. Now, I'm going to make this a generic atom now that has some electronegativity, right? Now, let's say we have I don't know, 3 atoms that kind of find themselves near each other. And they all have slight electronegativity differences. And let's say this guy here has an electron around the outside that these are not very good atomic models. Of course, I'm just trying to make my point very simple in what I'm drawing. It's possible that this electron might start to be shared with all of these, right? And of course, the electron itself is not orbiting these, it's kind of buzzing about in its shell, but the orange line I've drawn represents the shared covalent bonds, right? When electrons are shared, it creates covalent bonds. In a ball and stick model, this molecule right now would look like this, right? And those lines representing these bonds, and the orange line kind of showing that the electron is moving about all 3 of them, right? Now, if the electronegativity difference between these is enough to create this sharing, but not enough for any of these to steal electrons away, then we're going to have what are called nonpolar covalent bonds. And a nonpolar covalent bond is simply that the electron is being shared evenly. Like if I were to freeze at random points as I'm doing this, it's equally likely that we find the electron around any of these 3 atoms, and these bonds would be nonpolar, right? Polar suggests having poles, like a North Pole and a South Pole, like magnetic differences. And so by nonpolar, we're saying it's remember, the electron carries a negative charge. So if there was more electrons over here, this would be a little more negatively charged than this. And with a nonpolar covalent bond, we're saying there's no part of this molecule that's any more positive or negative than another because those electrons are moving about evenly. Those electrons that carry that negative charge, right? Now, let's say that we're going to have the same interaction, basically, and there goes my camera. Let's say we're going to have the same interaction now, but this time the electronegativity difference between the 3 is a little greater. In other words, there's more of a difference in how bad they want electrons. Let's say this guy here wants the electrons more. Right? If we have an electron that's, again, shared, right, but has a stronger pull here, it might be a model that looks something more like this. So the electron's still going around evenly, but it's more likely to be found here. And now suddenly we have a slightly negative charge on this side and a slightly positive charge here. And now what we've created is what's called a polar molecule. And again, we'd still have the same bonds, but now that this molecule is not charged. We would not call this molecule charged. We would say it has an uneven charge. It's polar. And so polar covalent bonds form when the electronegativity difference between two or more atoms is a little bit greater, but not too great, as we're about to see. So that's polar. And some of you might remember that water is a great example of a polar molecule. We're going to also emphasize that glucose is a polar molecule. Okay, so now let's say these same three atoms get together and the electronegativity is much higher in this one than the other two. It probably actually makes more sense in this example just to have the two atoms, just to make my point a little clearer. So let's say that now the electronegativity is so different an electron gets stolen or completely transferred. So let's say that this element, for example, is sodium, and this element is chlorine, right? If these two bump up against each other,